A buffer solution is a solution that resists the change in pH when a strong acid and base is added. So if you memorize your strong acid and bases, it is present. The first thing you need to do is write a neutralization reaction. The neutralization reaction will consist of your acid plus a base. This is going to yield water and a salt. This will be a double replacement reaction. If the base is strong, the acid will be a weak acid. If the acid is strong, then the base will be a weak base. Either or, it will be a double replacement reaction in which water will be created and salt. After you write your neutralization reaction, you write a BCA table. This is before, change, and after. In the table, we are determining how many moles of acid and base are neutralized. So the math must be calculated in moles, and you must determine the limiting reactant. And as before, the left side, you will subtract the limit, and on the right side, you will add the limit. Afterwards, depending on what is present, you will write an equilibrium equation, either an acid dissociation or a base dissociation most of the time, unless there is no more weak acid or base left over. Afterwards, you would do an ice table for equilibrium, and you could either solve it using the equilibrium expression, products over reactants, using the Ka or Kb, or you could use the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation is another way to find the pH of weak acid or weak base from its dissociation constant. The general formula is pH is equal to pKa plus log of A minus, which is the conjugate base, over its acid. For POH, it is pKb plus log of the conjugate acid over the base, or the weak base. From the previous video, P means negative log of the Ka, or the acid equilibrium constant, or the acid dissociation constant. POH is equal to pKb, which is negative log of Kb, which is the dissociation constant for bases. At midpoint, or a half equivalence point, the number of moles of the conjugate pair are equal. So the log of 1 is equal to 0. So the equation becomes pH equals to pKa, or the negative log of Ka, or POH becomes pKb, or the negative log of Kb. You do not have to use the Henderson-Hasselbalch equation. You could also use the equilibrium equation to solve for the value. However, at midpoint or half equivalence point, which we'll spend more time on the titration unit, it is a lot faster because pH is only negative log of Ka and POH is the negative log of Kb. Pause the video, solve this problem on your own, and then check your answer. This problem is just a regular dissociation of an acid. So we're going to start with our acid because Ka is provided. So we have HOCl, which is going to dissociate partially into H plus AQ plus OCl minus AQ. We're looking for the pH, so we have to do an ice table at equilibrium. Initial concentration of HOCl is given as 0.165 molar. H plus and OCl minus are 0. These are all 1 to 1 to 1, so this is going to be minus X plus X plus X. To find equilibrium, we have to add the I and C together. So 0.165 molar minus X, X, X. Now we're going to write the equilibrium equation. So Ka is products over reactants. We have H plus times OCl minus over HOCl. Plug in, so that's going to be X times X over 0.165 molar minus X. This is equal to the K, which is 3.0 times 10 to the negative 8th. I'm going to assume the 5% rule. So the negative X is going to approach 0. 7.0356 times 10 to the negative 5th molar. With 2 sig figs, it's 7.0 times 10 to the negative 5th molar. This is the concentration of H plus and the concentration of OCl minus at equilibrium. So we're going to see if the 5% rule is valid. So percent is equal to dissociation over initial concentration times 100. This is equal to 7.0 times 10 to the negative 5th molar divided by 0.165 molar times 100 equals to 0.042%. So since this is less than 5% dissociated, the 5% rule is valid and we could cross out the negative X. Now we need to calculate the pH. pH is equal to negative log of H plus, which is equal to negative log of 7.0 times 10 to the negative 5th molar. This is equal to 4.1549. Sig figs for pH starts after the decimal. There are 2 sig figs, so it's going to be 4.15. Pause the video, try part B on your own, and then check your answer. So for this solution, 14.3 grams of calcium hypochlorite was added to 1 liter solution. So the first thing I need to do is calculate the molarity of calcium hypochlorite to use as a common ion effect. So we need to calculate the moles of calcium hypochlorite. So we have 14.3 grams of calcium hypochlorite. Diagonal units have to be the same. To convert to moles, I need to do molar mass, so 1 mole of a substance must equal to its mass in grams, which is 142.974 grams. Diagonal units cancel out. Since we are doing the common ion effect, we don't need calcium, we need OCl, the hypochlorite ion. So diagonal units have to be the same, so this is going to be 1 mole of calcium hypochlorite. In 1 mole of this compound, there are 2 moles of the hypochlorite ion. So this equals to 0.200 moles of OCl minus. So the new concentration is moles over volume. That's going to be 0.200 moles over 1 liter, because that was the volume given, over 1 liter, because that was the volume given of solution. So the concentration is 0.200 molar OCl minus. So I start with the ice table. Since I have the acid, I'm going to start with the acid and dissociate it into its ions. The acid has the initial concentration of 0.165 molar. We have no H plus, but my OC minus is 0.200 molar. So this is a 1:1:1 ratio. So this is going to be minus x plus x plus x. Equilibrium is the addition of IC. We're going to write the Ka equation, which is products over reactants, which is H plus OC minus over HOCl. If I plug this in, this is x plus x for OCl minus divided by 0.165 molar minus x. This is going to equal to 3.0 times 10 to the negative 8, which is the Ka of HOCl. We could assume the 5% rule because our exponent is times 10 to the negative 8. And even in the first problem, when we did the 5% rule, it was less than 0.04%. So here too, we could assume the 5% rule and don't even have to check it later because our exponent is to the negative 8th. So if I solve for x equals to 2.4 times 10 to the negative 8th, which is really tiny. If I subtract from 0.2, it doesn't even affect the answer. Molar. So this will be your concentration of H plus. So to find the pH of this solution, pH is equal to negative log of H plus. This is negative log of 2.4 times 10 to the negative 8th molar, which equals to 7.6197. We have 2 sig figs, so I need 2 after the decimal. So right here, I like 1 to the right, so this 1 will become a 2. So 7.62 is the pH. This is method 1. You could also use the Henderson-Hasselbalch equation, which is a little bit faster. So Henderson-Hasselbalch says pH is equal to pKa, because this is an acid, log of the conjugate base over the weak acid. And the conjugate base is the A minus, the weak acid is the HA. This is at equilibrium. pKa, that's negative log. Remember, P means negative log of 3.0 times 10 to the negative 8th molar plus log of the conjugate base. The conjugate base here is OCl minus. My weak acid is HOCl. My exponent is negative 8, which is really tiny. So this is approximately 0 as we calculated up here, right here. So I'm going to plug my numbers in. So my conjugate base is going to be 0.200 molar divided by my conjugate acid, which is 0.165 molar. This is equal to 7.6064. And again, there's 2 sig figs. I look 1 to the right. 7.61. My answers are very close to each other. They're almost the same. Either method works. Would the value of H3O plus, the hydronium ion, increase, decrease, or stay the same if 0.74 grams of calcium hydroxide was added to the 1.0 liter solution? Show work to support your answer. We have a solution and we are adding a strong base. And what does the buffered solution does? It resists the change. Since a strong base or acid is added, we must do a before and after to determine the limiting reactant. So we need to write a neutralization reaction, which is between the acid and base. So the acid here is HOCl plus the base, which is CaOH2. This is going to be a double replacement reaction. H2O plus CaOCl2. Since calcium hydroxide is a strong base, it breaks down into Ca, 2 plus, and 2 OH minus. This is also soluble, so it's going to break down into Ca2 plus and 2 OCl minus. Since the calcium ions are spectator ions, they cancel out. So my equation is actually HOCl plus 2OH minus yields HOH. I'm going to rewrite water this way, plus 2OCl minus. Now I need to balance my equation. There's one H on the reactant side and one H from the water. On the acid side, there's one H and one OCl, and then two OHs. To balance this, I need to remove the 2's. So this is the balance equation, and I need to do a before, change, and after. In order to do this, we need to calculate the moles of each of the acid and base. There are 0.74 grams of calcium hydroxide. We need to convert this into moles, so I need to do molar mass, so grams. This is grams calcium hydroxide to 1 mole of calcium hydroxide. The mass is 74.08. That cancels out. We need OH ions, so I need to continue on. Diagonals have to be the same. This is moles of calcium hydroxide. In 1 mole of calcium hydroxide, there are 2 moles of OH minus ion, 0.01997. We need 2 sig figs, so it's going to be 1, 2, I leave 1 to the right, so this is going to be 0.020 moles of OH minus. We also need to find the moles of the acid. We started with 1 liter of solution, and there is 1 liter, 0.165 moles of HOCl. So this is going to equal to 0.165 moles of HOCl. Now I'm going to fill my BCA table up. The moles of HOCl is equal to 0.165 moles. The number of moles of OH minus is 0.020 moles. Water does not count because water is in the liquid state, and then OCl minus started at 0. Since we are neutralizing, what we are doing is for every mole of acid, there is a mole of base, and they cancel each other out by neutralizing each other. So if I look at this table, my limiting reactant is OH minus, because I have only 0.02 moles versus the acid I have 0.165. So I need to subtract by my limit on my reactant side and add on my product side. So to find it after, I need to add B and delta, or change in. This is 0.165 moles minus 0.020 moles, which equals to 0.145 moles. My base is complete use up, so I have 0, and my salt ion and my conjugate ion is 0.020 moles. So now I have the acid and its conjugate base present. So my equilibrium equation for my ice table will start with my acid dissociation. HOCl AQ is going to ionize or dissociate partially into H plus AQ plus OCl minus AQ. So my ice is table. Initial concentration is not 0.165. It is going to be 0.145 0.45 moles, because that is what I have left over, divided by my volume, which is 1 liter. My H plus, I still have 0. My OCl minus is not 0. I have 0.020 moles left over 1 liter. So now my buffer solution is kind of like a common ion effect. Since everything is 1 to 1 to 1, on the reactant side I'm going to subtract by X, product side I'm going to add by X. So equilibrium is IC added together, so this is going to be 0.145 molar minus X, X 0.020 molar plus X. If I use the Ka equation, this is equal to H plus times OCl minus over HOCl. Plugging in, this is X 0.020 molar plus X 0.145 molar minus X. This is going to equal to 3 times 10 to the negative 8th. I'm going to assume this is going to fall into the 5% rule because my exponent here is so small, so this approaches 0. X equals to 2.175 times 10 to the negative 7th molar. This is my H plus concentration. With correct sig figs, I need 2, so this is actually 2.2 times 10 to the negative 7th molar. I need to find the pH. pH is equal to negative log of H plus. So this is negative log of 2.2 times 10 to the negative 7th molar, which equals to 6.66 with correct sig figs. This is the pH of buffer solution. I'm going to also calculate this using Henderson-Hasselbalch. Since this is pH, this is equal to pKa plus log of its conjugate base over its weak acid. So P is negative log of my Ka, which is 3.0 times 10 to the negative 8th, plus the log of my conjugate base at the ice table, which is this, and we could ignore this because our exponent is so large. You could even double check by the 5% rule and you'll realize it's really tiny. We could ignore this. So this is my equilibrium for my weak acid, 0.020 molar divided by 0.145 molar, which equals 6.66 with correct sig figs. If you notice, the answers match here. So either method is correct.